We'll do one more example of a graph together. Let's take a look at analyzing and sketching the graph of f of x equals 1 divided by 1 plus e to the negative x. We'll start off by doing a lot of the things we did in the last section. First of all, we want to define the domain. We do have a denominator here, so we do have to be a little bit careful. When is 1 plus e to the negative x equal to 0? To solve this, you would subtract 1 from both sides. We would get e to the negative x equals to negative 1. And at this point, most of you can stop and realize that there's going to be no solution to this. The exponential function is always positive. It's never 0, nor would it ever be negative. If you wanted to algebraically continue it, what you would do is take the natural log of both sides to get rid of the e, and then you would see that the natural log of negative 1 as a calculation is undefined. So what does that mean? Well, for the domain, there's no restrictions, which means the domain is going to be everything from negative infinity to positive infinity. Okay, so that's good to know. Let's see if we can find some intercepts. We'll start by looking for x-intercepts. We set f of x equal to 0 and solve. When is 1 divided by 1 plus e to the negative x equal to 0? Well, you clear fractions, you multiply both sides by the denominator, and we would get that 1 is equal to 0, which is a contradiction. So there's no solution to that equation, which means that there are no x-intercepts. This graph will not cross the x-axis. To find the y-intercept, we just evaluate f of 0. If I plug 0 into the function, f of 0 is equal to 1 divided by 1 plus e to the negative 0. E to the 0 is 1, and so we would get 1/2. So we do have a y-intercept. It's going to occur at 0, 1/2. So x-intercept, we have none. Y-intercept is 0.5. The next thing we're going to look for is for our asymptotes. We saw that there's no values that make the denominator 0, so there will be no vertical asymptotes. To find the horizontal asymptotes, this is a little bit different. This isn't a rational function, so it's not just a matter of comparing powers. We have to do something else. Technically, when we're looking for horizontal asymptotes, these are the limits at infinity. So let's investigate the limit as x approaches negative infinity of 1 divided by 1 plus e to the negative x. In order to find this limit, if you wanted to, you could always rewrite it in terms of e to the positive power of x. But what do we know happens? The graph of e to the negative x looks like this. As x approaches negative infinity, the graph of e to the negative x is going to get larger and larger and larger. Adding 1 to it's not going to really do a whole lot. But essentially the denominator of this fraction is getting larger and larger and larger, while the numerator stays the fixed constant 1, which means that it's going to get smaller and it's going to approach 0. So we will have one horizontal asymptote. That's going to be y equals to 0. We also want to investigate what is the limit as x approaches positive infinity of 1 divided by 1 plus e to the negative x. Well, let me just re-put that graph on here again. As x approaches positive infinity, the e to the negative x term is going to approach 0. So this thing's going to approach 1 divided by 1 plus 0, which is equal to 1. So we have yet another horizontal asymptote. It's going to be y equals to 1. So we know our domain, we have our intercepts, we have our asymptotes. Let's now go ahead and find intervals of increase and decrease. So we want the derivative. Many different ways you can approach this. I'm just going to use a straight up quotient rule. You could actually avoid the quotient rule if you wanted to. You could do a chain rule if you take the whole denominator to the negative first power. But it's not too bad. The derivative of the numerator is 0 times the denominator minus the numerator times the derivative of the denominator. That's going to be e to the negative x times negative 1, all divided by the denominator squared. 1 plus e to the negative x squared. Just simplify a little bit, clean it up. We get that this term is 0. The negative will make a positive e to the negative x, all divided by 1 plus e to the negative x squared. So let's find our critical numbers. We want to find where f prime of x is equal to 0. If you set that fraction equal to 0, you would clear off the denominator. It's going to boil down to wherever the numerator is equal to 0. And we just said a moment ago that e to the negative x, or e to any power, is never going to be 0. So there's no critical numbers of the type f prime equals to 0. We could also try to investigate where is f prime going to be undefined. That would involve setting the denominator equal to 0. Take the square root of both sides. We would get 1 plus e to the negative x equal to 0. Subtract 1 from both sides. We get e to the negative x equals to negative 1. And that too will again have no solution. So this particular function does not have any critical numbers. What that means for us in terms of our sign chart is we have nothing to plot. We get the entire real line is one expression here, which means that the derivative is going to have a consistent sign on the entire real line. You can use any point for your test point. Let's just plug in 0. If I look at f prime of 0, this would be e to the negative 0 divided by 1 plus e to the negative 0 squared. Remember, e to the 0 is 1, so that's going to be 1 divided by, we get 1 plus 1 squared, which would be 2 squared, which is 4. But in particular, it's positive. So the derivative is positive, which means that this function is going to be increasing on the entire real line. So our function is increasing from negative infinity to positive infinity, and is decreasing nowhere. There's no place where this function is going to be decreasing. Okay, so we have that. The next thing we would want to do is now look at concavity and possible inflection points. So let's go ahead now and find the second derivative. So I have my f prime of x equals e to the negative x, all divided by 1 plus e to the negative x squared. To find that second derivative, we're going to go ahead and use the quotient rule again. F double prime of x should be equal to the derivative of the numerator, which is going to be negative e to the negative x. The derivative of e to itself is just e. Keep the power the same. And from the chain rule, that's where that negative sign is coming from. The derivative of that exponent, the derivative of negative x, is just negative 1 times the denominator minus the numerator times the derivative of the denominator. To do the derivative of the denominator, that's going to be a chain rule. Bring the power 2 down. Leave the inside part alone. Reduce the power by 1. And then from the chain rule, multiply by the derivative of the inside function. And that's going to be negative e to the negative x, all over that denominator squared. That's 1 plus e to the negative x squared squared. we have the f double prime of x is equal to. In order to simplify this, let's pull out a GCF from the numerator. In the numerator, and maybe we'll just let's combine a few things first here, just so it's not so much. We have a negative e to the negative x times 1 plus e to the negative x squared. A negative and a negative will make a positive. We have 2 e to the negative x times e to the negative x is e to the negative 2x. Multiplication by like bases, you add the exponents. And then we have a 1 plus e to the negative x. All over 1 plus e to the negative x, now to the 4th power. In the numerator, there's a common factor. I can not only pull out an e to the negative x, but I can also pull out a 1 plus e to the negative x. And because the first term is negative, let me actually factor out a negative GCF from that numerator. When I factor it out of the first term, what we're left with is a 1 plus e to the negative x, now to the 1st power. Subtract, this is now going to be a 2. If I pulled out one of the e to the negative x's, I'll still have a negative e to the negative x here. And then this factor here, that's what's pulled out, so now it's gone. This factor will cancel with one of the ones in the denominator. And so we have that f double prime of x, after all of that, is equal to negative e to the negative x bracket 1 minus e to the negative x all over 1 plus e to the negative x cubed. Okay. So this is the expression for our second derivative. We would now want to solve for where is f double prime equal to 0. Again, that fraction's only ever going to be 0 when the numerator is 0. So I can set the numerator equal to 0, like this. It's already factored, so we can set each factor equal to 0 independently. That is negative e to the negative x equals to 0, and 1 minus e to the negative x equals to 0. This part will provide no solution. If I add e to the negative x to both sides, I get 1 equals positive e to the negative x. I can take the natural log of 1 of both sides. The natural log of 1 is 0. The ln and the e cancel, so I get negative x equals to 0, or 0 equals 2 to x. So there is one place where the second derivative is equal to 0. You should also check to see where the second derivative might be undefined. We've seen this kind of equation a bunch already in the same problem, but if you set that denominator of the second derivative equal to 0, that will not provide any solutions. Okay. So we just get one place where the second derivative is equal to 0, and that's precisely at x equals to 0. We now want to plot that on a number line and do a sign chart for our second derivative to determine concavity. For example, if we plug in a test point in region 1, I would say probably let's use x equals to negative 1. F double prime of negative 1 would be equal to the negative of e to the negative of negative 1 times 1 minus e to the negative of negative 1, all divided by 1 plus e to the negative of negative 1 cubed. This is the negative of e times 1 minus e, all divided by 1 plus e quantity cubed. You can punch this into your calculator if you want. The denominator is positive. E is bigger than 2, so that factor is negative. This factor is negative, and a negative times a negative is a positive. So the numerator is positive, denominator is positive, which means that this whole thing is going to be positive. So the second derivative is going to be positive. And if the second derivative is positive, that means that the graph is going to be concave up. I'll leave it up to everybody to test it on their own, but a good test point in region 2 might be to use x equals to positive 1. Guaranteed, if you try f double prime of 1, that should be less than 0, which means that the graph is going to be concave down there. So we have answered concavity. The graph is concave up from negative infinity to 0, concave down from 0 to positive infinity, and because we have a change in concavity, that means that at x equals to 0, there's going to be an inflection point. At x equals to 0. Luckily for us, we've already plugged this in earlier. We plugged 0 in as our y-intercept. So at 0, 1/2, we're going to have an inflection point. Okay. That should give us everything we need now in order to create a detailed graph of this function. So first things first, I'm going to start off by plotting any points that I have. We have the point at 0, 1/2. It should be about here. It's not only a y-intercept, but it's also an inflection point. The next thing you would want to do is plot any asymptotes. We have a horizontal asymptote at x equals to 0, y equals to 0. That would be like this. And also at y equals to 1. We know that the graph is increasing forever, and it's going to have to follow the asymptotes. So it's increasing, and it's concave up from negative infinity to 0. And then after we pass 0, from 0 to positive infinity, it's still increasing, but it's going to be concave down. And so this would be the graph of our function in example 2.